This section deals with alternating series and what it means to alternate. So in a series, we have successive terms being added together. But when the series alternates, then we have this pattern of plus minus plus minus plus minus, or minus plus minus plus minus plus. Something like that when we have an alternating series. So let's first talk about what sort of mathematical expressions cause alternating signs. So we need something that's going to cause a sign to go from plus to minus. And of course, multiplying by a -1 would cause something to go from a plus to a minus, or a minus to a plus. So if we can get this to alternate between -1 and 1 and -1 and 1, without changing the value, then we can put that in front of a term and not affect the value of the term, but just affect the sign of the term. And the way we do that is to just raise it to the power n. So when n equals 1, this expression equals -1. When n equals 2, that expression equals, I forgot the negative sign there, that expression equals 1. When n equals 3, that expression equals -1, and so forth. So that's one way to get an alternator. And anything that's going to cause this power to increase sequentially. So for instance, not only does -1 to the n power work, but -1 to the n plus 1, or -1 to the n minus 1 would also work, depending upon what you need to start off with. So starting here for an n value of 1, we could start here with the first value being a positive instead of a negative, where this first value started with a negative. So this would end up, if we start at n equals 1 and go to infinity, we could start off with a positive value that way. So those are 3 really popular alternators. We've got this one and these as well. Okay, and then so we have to think of these things that kind of cycle, so to speak. And so another really popular alternator would be a trig expression. So for instance, if we take a look at cosine and sine, cosine is 1 at 0 radians, and it's -1 at pi radians. So if we can get an expression that gives us multiples of pi, we could again fluctuate from -1 to +1 and so on and so forth. So we could say we would have to have multiples of pi, so n times pi. Or likewise, sine is 1 at pi over 2 radians, and sine is -1 at 3 pi over 2 radians. So this one gets a little more complicated, which is why we really prefer cosine, because we have to go from 1 pi over 2 to 3 pi over 2, so we have to count by odds. And so in order to count by odds, odd powers of pi over 2, we're going to have a counter over here that counts by odd powers, and that might look something like 2n minus 1. So when n equals 1, this is 2. When n equals 2, when n equals 1, this is 2 minus 1, which is 1, so we have sine of pi over 2. When n equals 2, 2 times 2 is 4, minus 1 is 3, so we have sine of 3 pi over 2, and so on and so forth. So that would be a way to use trigonometric functions to get an alternator as well. So kind of just to recap here, to get alternators, we've got -1 to the n, we've got -1 to the n plus 1, we've got -1 to the n minus 1, we've got cosine of n pi, and we've got sine of 2n minus 1 times pi over 2. So those all, they look very different, but they're all really just a way to get the sign in front of the term to oscillate between negative and positive. So now that we have our different methods of getting the sign in front of the term to oscillate back and forth between -1 and 1, I'll just write those ways up here again. That helps us identify what the alternator in the series is. So, and that's important because the alternator is just something that's going to affect the sign. It's not going to affect the term itself. It's not going to affect convergence or divergence per se. It just is going to dictate that sign. And so when we talk about an alternating series test, an alternating series is then comprised of two components. We have the alternator, so that alternator is going to look like probably one of those 5 forms. And then we have the term for the nth expression, so we have the nth term. And so what we take a look at then is we take a look at, it's kind of a 2-part process. We talked about taking the limit and the limit being equal to 0, taking the limit of the nth term. And so this arises from the failure of the nth term test to be a test for convergence. So if you remember back to section 2, the nth term test said that if a sub n does not equal 0, the series diverges. So that's what the nth term test said. So basically, when a sub n equals 0, the nth term test fails. And you know, I've mentioned it several times. When we get an inconclusive result, there we go, an inconclusive result when we do a test, all that means is that we chose the wrong test. So when the nth term test fails, the indication then would be to try the alternating series test. Okay, so the alternating series test is saying, let's go ahead and determine the limit of the nth term. And if it's 0, then we have to prove that we have a series that gets smaller and smaller and smaller. So the n plus 1 term is less than or equal to the nth term. And then if those two criteria are met, then we know that we have a convergent series. So if we think about this, what the limit of a sub n equaling 0 means, that means, you know, as we write our terms on and on and on, eventually we end up adding 0, adding 0, adding 0, right? That's what that means. Or in the case of an alternating series test, we end up adding 0 and subtracting 0 and adding 0 and subtracting 0. So obviously, if we're going to run into this scenario, then these zeros will cancel out and these zeros will cancel out. And so we know we've stopped contributing to the sum. We can then call it a convergent series. If you remember back with when we didn't have alternators, we said we didn't know if it pinched off fast enough. And that gave rise to the integral test and the p-series test. So, so as long as we have this, remember this is less than or equal to, so we call this non-increasing. So as long as we have this non-increasing phenomenon, and we have this next value that is smaller than the previous value, then we can go ahead and smaller than or equal to, then we can go ahead and call it convergent, call the alternating series convergent. So taking a look at this example here, here's our alternator. So there's our alternator. And really all our alternator is saying is that we should be looking to use the alternating series test. So really use that as kind of a red flag. That's why I'm using red here. Kind of a red flag to say, hey, use the alternating series test. It's the only test that is set up for things that fluctuate between plus and minus. So the a sub n then, the nth term, looks like everything here without writing down the alternator. So the nth term is n over 2n minus 1. So we take the limit as n goes to infinity of n over 2n plus 1, and we evaluate that. And that's easy enough to do L'Hopital's on. You only have to differentiate once, which is nice. So the limit as n goes to infinity, derivative of the top is 1, derivative of the bottom is 2. And when we evaluate that, it's not 0, it's a half. Okay, so a bit of a trick question to start off with. Okay, what we just did then, as long as we did this and we got not 0, then we can say that the series diverges. We just basically did the nth term test. So even though this is an alternating series, even as it's alternating, we're perpetually adding a half. And so what happens is, and I'll talk about reaching the sum in a second, but basically we perform the nth term test. So this diverges by the nth term test. So if you think about, say test. So if you think about perpetually adding a half, right, we've got this a sub 1 term plus, actually minus since it's alternating, this a sub 1 term minus this a sub 2 plus this a sub 3 minus this a sub 4 plus dot, 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 dot. And then eventually we end up going minus a half plus a half minus a half, etc. And so what happens to the sum is the sum reaches some finite value, but then starts to oscillate. So, you know, the sum might reach some value, but then it starts to do this. Plus a half, minus a half, plus a half, minus a half, plus a minus. So the sum oscillates. And by definition, if the sum oscillates, then it can't converge because it never settles on one value. So for this question here, we haven't used the alternating series test yet. We tried to use the alternating series test because we saw the alternator, but the first part of the alternating series test failed. So I'll just kind of make that note here. First part of AST failed, and therefore we have a divergent series by the nth term test. Okay. So before we go on to the next example, I just kind of want to reinforce this idea that the alternating series test is for convergence only. So we talk about this phenomenon of testing for convergence or divergence. You know, for instance, geometric series test, we can test for convergence when the common ratio r is less than 1, or we can test for divergence when the common ratio r is greater than 1. For the p-series test, we can, in fact, let me just kind of break this summary down. For the geometric series test, we can test for convergence, absolute value of r is less than 1, or we can test for divergence. Absolute value of r is greater than or equal to 1. For things like p-series test, we can test for convergence, right? P is greater than 1, or we can test for divergence. P is less than or equal to 1, right? This came out of the integral test, and that 1 over n series is that transition point from converging to diverging. And that's a 1 over n to the one power, right? Because the p is the power, and this is the AR to the n sort of thing. And of course, the p series test came out of the integral test. And we can test for convergence as long as we can find the area, and we can test for divergence if the area goes to infinity. And so what people kind of really get in the habit of saying is, well, it's convergent if we can find some finite sum, which is true, and it's divergent if things go to infinity, if the sum goes to infinity, which is also true. So we can find some finite value here for convergence, and that's very true. Or, then if it's divergent, the sum goes to infinity. And so what a lot of people don't really realize, or what they don't do, is they don't extend their thinking here. Not only can it go to infinity, but it can go to minus infinity. And not only could it go to those two values, but it could oscillate. In either of three of these situations, what's happening is we have a sum that is not settling on a single value. And that really is the true meaning of divergent. It's not going to settle on a single value here because infinity is not defined. Ditto for negative infinity, and ditto for oscillating between two values. None of these cases allows that sum to settle on a single value. So that's really the full spectrum of divergent series. So when we get to the alternating series test, and we talk about the nth term test, if you notice, the alternating series test tests for convergence only. So we have this limit as a sub n, limit of a sub n as n goes to infinity equaling 0. And then we've got this a n plus 1 less than or equal to a n. And then and then we don't have any test for divergence. Because what happens is, as soon as we fail in part 1, we've performed the next test. The limit as n goes to infinity of a sub n not being equal to 0. We've performed the nth term test. So, and the nth term test we can't use for convergence, because if this equals 0, then we're inconclusive. And so what we do is we use these two tests kind of in conjunction with one another, so that and so they kind of function as a single one of these. As a pair, we can use one for convergence and the other for divergence. For this series, this is where the alternator can kind of hide on you. But we notice we have a trig function here, cosine of nt. So there's your alternator. So that's going to fluctuate from 1 pi to 2 pi to 3 pi. So it's going to fluctuate from, let's see, cosine of pi is -1, right? So it's going to fluctuate from -1 times 1 over 1, which is -1. And then when we put n equals to 2, then it's going to be 1. So it's going to be plus a half. And then n equals 3 minus a third plus a fourth. And so we know, we've talked about 1 over n before, right? 1 over n by itself is just a p series. So even before we look at this, let's just kind of split this in half here and look at the series n equals 1 of 1 over n, okay? That's a p series. P is equal to 1. And so this must be divergence, right? Because the criteria for divergence is p less than or equal to 1. So we know that this diverges. Now this is 1 plus a half plus a third plus a fourth, ... So this is successively adding fractions, where this series is starting at -1 and adding a half. So coming up to -1/2, then going back down to -5/6, then coming back up again closer to 0. So so this one starts to alternate, So as we look at the alternating series test here, I usually just number my two criteria. I'm going to go ahead and take the limit as n goes to infinity of 1 over n, right? That's the, in fact, let me change colors here. This is my a sub n, and let me just change those colors. Go ahead and go to green. Oh, this is the right green here. Must be that one. Okay, there we go. Okay, and so so the limit as n goes to infinity equals 0. Okay, so that we passed part 1 of the test. We have to have this limit go to 0. We have to have this eventually be plus 0, minus 0, plus 0, minus 0, so the zeros can cancel out. The next thing then is we have to prove that the next larger term is less than or equal to the previous term. So we have to do a little bit of a mathematical proof here. And so this whole thing is saying basically I want to get to a point where I'm plus 0, minus 0, plus 0, minus 0. Or if it's a number that we're adding, then it's plus 4, minus 4. I shouldn't even say that. It's just plus 0, minus 0, plus 0, minus 0. And so a sub n is 1 over n, less than or equal to, or greater than or equal to, if I'm writing this backwards. The next bigger term is 1 over n plus 1, right? So we started with 1 over 1, then 1 over 2, then 1 over 3, then 1 over 4. So we have to prove that this is in fact the case. So it just takes a couple of steps to do. We can cross multiply. So we get 1 times n, which is n, and 1 times n plus 1. So n is less than or equal to n plus 1, which is true. We don't need to say anything else other than the fact that this is littler than this. We could take it one step further. Let me just give you an option here just to kind of help you rationalize it. We could subtract n and say 0 is less than or equal to, we've got 1 left here. That is definitely true. And so if you want to take it, oops, no, e indefinitely. There we go, definitely true. Or is there an e indefinitely? I'll let you decide. That's my spelling. So 0 is definitely less than or equal to 1, so that proves that this is a non-increasing series. So we can conclude then the series with the alternator. Whoops, and I wrote the wrong alternator. I just realized that. Cosine of n times pi, as n goes from 1 to infinity, diverges, wow, that's not right, converges, because of the alternating series test. And AST is used for alternating series tests. It's kind of pretty commonly known.